So now for case 1, I'm sorry, before I start this, let's make things clear, okay? Previously I named all this as case 1 and case 2, right? Now I'm gonna name whatever that I've started earlier is case 2 and case 3. So the first one I did is actually this one, right? So we call this case 2 because correspondingly for your math, okay, this is case 2, okay, when your damping factor is critical damping, okay, is equals to 1. And then for under damp, deals with the complex issue, you're gonna deal with the case 3, okay. So now we go to the case 1. The reason why they actually do it in terms of another way is because they want to start the things by hardest to easiest to explain. So for this case, over damp is very easy to explain. Simply we no need to derive. In fact, we don't need to derive anything. Okay, we're just knowing the concept. Okay, this is because, as I say earlier, you sub in your damping factor into general equation, then you get and then you derive a displacement x with a variable natural frequency. With a variable, you derive an equation that has variable that are natural frequency and damping factor. In this case, the very general equation for ours is already in terms of natural frequency and natural frequency and damping factor. It's just because the damping factor itself is different. That's why if it's equals to 0, we have a problem. Okay, the problem for the case 2 itself is that if you remember, everything goes to 0. Okay, everything goes to 0, and then we cannot solve. That's why we introduce the BT. Okay, as we introduce this equation as our solving equation. Yeah. So in this case, yeah. So as you can see, and then for the case 3, right, it's because when you sub when this is become negative, we will also have a problem, which is the complex issue I. So we need to get rid of the I in order to go back to the natural frequency and the damping factor, damping ratio equation, which is this. And therefore, in our case, for case 1, it is just simply um, this thing, because we just use this. So 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 just as a summary saying is that the previous equations for case 2 and case 3, right, is because when you sub in your naming factor, you meet certain problem in your equation. That's why you need whatever thing that I have just derived. Okay. So because after you sub in your damping factor, okay, after you sub in your damping factor, you realize that there is a lot of problems, and therefore you need a derivation to have another type of equation to solve for whatever thing, to solve for your displacement x. Okay, so this is clear. And then for over them, is because there is no problem in anything, because this equation itself is a general equation by itself. Therefore, you just sub in your 1. I mean, rather than 1, you eventually get whatever you want. Okay. So yeah, and then another thing, and then I haven't explained how this graph move. Okay. So in this case, if this is because damping factor square is larger than 1, so this is real ma. So as x um approaches 0, as t approaches infinity, okay, as x approaches 0, okay, I mean as this amplitude decay, okay, as this amplitude decay and t approaches infinity, in other words, how do I say it? Okay, give me a minute. And yeah, I anyway, so okay, just a summary is that when for over then you use this equation, you can find your displacement amplitude x. That's all. Okay, nothing much. The graph itself, the higher your damping factor, okay, this is equals to 1. Okay, equals to 1 is like that. And then larger than 1, it's there is no oscillation. There is totally no oscillation. It could, when okay, maybe I should give me the red color itself is when damping is over damped, okay, which is case 1. Case 2 is critically damped, okay. There is no, for case 1 and case 2 there is no oscillation, okay. But for case 2 it is just nice that there is no oscillation, okay. And then for under damped, there will be oscillation and there will be a frequency, because when there's oscillation you definitely has to do with phase angle and frequency, and therefore the equation as I shown just now, yeah. So with this in mind, I think I've cleared all the stuff. So I just a quick summarize form for the whole derived viscous friction is that first we, at the very first part, we derive we introduce you um the we already derive the viscous damping, okay. We derive the viscous damping, okay. I'm just ending this part only, okay, just to let you know I'm just ending this part. I still got tutorial 4, part 4 to go. Damn, 2 hours of lesson, 7-8 hours of fuck. Anyway, so yeah, and then okay, what am I doing now? Oh yeah, just explaining to you the summary, right? So the first part we actually doing is to derive the general equation, and then you know that using our very holy resource, where is it? Stating that you have to first understand the motion of the spring, and then you draw a FPD stating all forces acting on the mass, the V size, the length, the point, the displacement, whatever you want, your initial condition, stating that summation of moment or summation of forces, in this case is summation of forces, and therefore we do that. So yeah, summation of forces, and then we do whatever thing that I've said earlier. You derive your general equation. Once you derive your general equation, okay, and also yeah, never mind. I also forgot what I said about here. But you derive your general equation, and if for general equation is to solve for your, if you got damping factor and your okay, once you get a general equation, sub in a damping factor, and then see whether is your equation an equation that is problematic or not. If it's not problematic, like over them, then you can just use the general equation to solve. If it's under them and critically them, you have to derive what I have derived earlier. Yeah, and this 2 videos. So I hope that I've made things clear for you, and the graph itself, as you can see the trend as I mentioned. This is the summary, and everything, all of the calculations, all of the equations, right? Even the general equation itself is calculating the amplitude x. That's all. Okay, the distance. We're just calculating the distance. The distance from when the mass is over here, when it is stagnant. Okay, when it's stagnant, and when you start to pull it down to this position, the difference in x is the x that I'm talking about. And this line is the datum, whatever datum you pick, relative to whatever datum, yeah, of the thing itself lah. Okay, see which x you are doing lah. So make sure you do it. But actually, this line is, sorry, this line should be here. Okay, this, yeah, top and top. Okay, the top of the surface of the mass and the surface of the mass should be, so this is x. So you have to pick your datum and everything, which I have mentioned lesson 1 and lesson 2. And in this lesson 3 it talks about all these things. So I hope I make things clear, and I'll just set off with tutorial 3 question 2, and then yeah, and then yeah, we are done. So yeah.